Hello everyone and welcome to Control Engineering Tutorials. In this tutorial we will solve one very important problem that every control or signal processing engineer need to know how to solve. Namely, in this tutorial we will learn how to use the pole placement method to select control algorithm parameters such that the poles of the closed-loop system are placed at the desired locations and such that the desired closed-loop behavior is achieved. More precisely, on the basis of the desired locations of the closed-loop poles, we will determine the parameters of the proportional integral derivative or PID control algorithm. We will also see that the control algorithm will introduce zeros in the closed-loop transfer function that will slightly degrade the desired closed-loop response. But before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 350 free video tutorials that you can find on my YouTube channel, and consequently I kindly ask you to press the like and subscribe buttons. Thanks a lot. Also, if you have any question or a comment about the material presented in this video tutorial, please feel free to leave your comment or a question in the comment section below this video tutorial. Thanks a lot. Here's the problem statement. We are given an open loop transfer function given by this equation, and we want to design a feedback control algorithm such that the poles of the closed loop transfer function are placed at these locations at -2, -3, and -4. Here's what we should achieve. Obviously, the poles of the open loop transfer function are on the imaginary axis. That is, one is at 2j and another one is at -2j. And we want to design a closed loop controller such that the poles of the closed loop transfer function are placed at -2, -3, and -4. Also, a very important design requirement is that the steady state error of following a step reference signal is asymptotically equal to 0. Let's solve this problem. The first step is to analyze the problem and to explain a few important things. As I mentioned previously, it should be observed that the open loop transfer function has poles on the imaginary axis. This is not what we want. Such a system exhibits an oscillatory behavior and cannot accurately track a step reference signal. Consequently, we need a feedback control algorithm to asymptotically stabilize this system and to make sure that the closed loop system can asymptotically track a reference signal. Also, we want to place closed-loop poles on the real axis. We want to place the closed-loop poles on the real axis mainly because we want to ensure a smooth system response with minimal oscillations. That is, we will see that these exponential terms will appear in our step response. However, we will also see that the controller will induce zeros that will induce some oscillations and overshoot in the response. Now we understand the requirements and we understand why the problem is formulated like this. The next step is to solve the problem. The first step in our solution is to construct the block diagram of the system. Here is the block diagram. W of s is our open loop transfer function, C of s is our controller, S is the Laplace complex variable, E of s is the error in the Laplace domain, and error is the difference between the reference signal and the output of the system. U of s is the output of the controller, that is at the same time the input to our open loop transfer function, and here is the feedback. Next, we need to determine the closed loop transfer function. The closed loop transfer function is derived from this equation. What do we do over here? We simply write the output as a product of our W and U. And we go one step back. we know that u is actually E times C, and we substitute these equation in this equation, and finally we substitute the expression for the error given over here, and we obtain this equation. From this equation, we obtain this equation, and from this equation, we obtain this very important equation. This is the input-output representation of our closed-loop system. R of S is the reference signal. This signal is the desired behavior of our output, and this signal is specified by the user. For example, it can be a step signal, it can be a ramp signal, it can be a sinusoidal signal, or it can be a combination of these elementary signals. We filter this input signal through our transfer function to obtain the output of the system. This transfer function is called the closed-loop transfer function, and it's given by this equation. Another very important concept that we need to define is the concept of the closed-loop characteristic polynomial. The closed-loop characteristic polynomial is obtained by setting this expression in the denominator of our transfer function to 0, and consequently we obtain this equation. From this equation we will obtain the closed-loop characteristic polynomial. Let's analyze this equation. W of S is given. This is our open-loop transfer function given by this equation. However, we have a complete freedom to choose our controller. In this video tutorial, I will select the proportional integral derivative or PID control algorithm. The transfer function of the PID control algorithm can be written like this. Over here, K, A, and B are the control parameters that we need to determine. To see that this equation is actually the transfer function of a PID controller, we can easily multiply these terms, and we can write the equation 10 as the equation 11. Since 1 over S is an integrator in time domain, S is the derivative in the time domain, and a constant term in the Laplace domain is a proportional term in the time domain. In the time domain, this equation has this form. And we can clearly see an integral term over here corresponding to this part, proportional term over here corresponding to this part, and derivative term corresponding to this part. Next, let us substitute our open-loop transfer function and our controller in this equation. As the result, we obtain this equation. By multiplying this equation by S multiplying S squared plus 4, we obtain this equation. And by multiplying the terms in this equation and grouping them together, we obtain this equation. On the other hand, our task is to assign the closed-loop poles at the following locations: -2, -3, and -4. From this, we conclude that the desired characteristic polynomial of the closed-loop system should look like this. How do we know that? Well, if we substitute S1 over here, we obtain 0. If we substitute -3 over here, we obtain 0. If we substitute -4, we obtain 0. That is, this is our desired closed-loop characteristic polynomial. By multiplying the terms in this expression, we obtain this equation. And finally, we obtain this polynomial. Now, we want to select K, A, and B such that this parametrized characteristic polynomial is equal to desired characteristic polynomial. And what do? We simply say this equation should be equal to this equation, and consequently we obtain this equation. We know that two polynomials are equal if their coefficients are equal. By using this fact and this expression, we obtain. Let's see, K is obviously equal to 24. Perfect. This term 4 plus Ka plus Kb should be equal to 26. Here's our second equation, and where's our third equation? Here it is. Kab should be equal to 9. Here it is. From the first equation, we immediately obtain that K is 24. And by substituting K is equal to 24 in these two equations, we obtain the set of equations in the equation 21. This is a system of two equations in two unknowns. The unknowns are a and b, and let's solve this system. Let us first multiply the first equation from left with the a, and as the result we obtain this equation. And over here we can see this term ab, so substitute ab in this equation, and finally you will obtain this equation. I will solve this equation in Python, and later on I will show you the code. The solution is given over here. Here it is. We have a1 and a2. Corresponding to a1, we also have b1. b1 is obtained from this equation by simply dividing this expression by a. And watch out, a is a complex number, and be careful when dividing the complex numbers. I do that in Python. And as the result, we obtain b1 and b2. So we have two sets of control parameters. We have this set and we have this set. If we substitute these control parameters, you can choose any set, for example, either this one or this one, and you substitute them in our PID controller equation, either in this equation or in this equation, you will finally obtain the PID controller. Here it is. Now, here you need to observe the following. The parameters a1 and b1 are complex. However, since we have multiplication of complex parameters, we will obtain controller that doesn't depend on complex parameters, and consequently this controller can be implemented in your digital computer. Perfect. Here's the Python code for computing the parameters a and b. First, we want to solve this equation over here, or better to say this equation. We can do it easily in Python by first observing that this is a polynomial in a, and we specify a list with the coefficients of this polynomial. We have 1 multiplying a squared minus 11 over 12 multiplying a, and 3 over 8 is just 3 over 8. Again, look at here. This is the polynomial, and this is the polynomial as a list in Python. And we simply call this function numpy roots to compute the roots of this polynomial. That is, we are computing zeros of this quadratic equation. Perfect. Let's do that. But before that, let me clear my workspace and let's see the results. Okay, so here are the zeros. Perfect. To compute the b coefficients, we need to go back in this equation. From here, we can express b as 3 over 8 divided by a. And we can do it easily in Python over here. And notice over here that Python automatically recognizes that these are the complex numbers, and it automatically applies the rules for complex number division. Okay, so let's see the results. And let's check. A1 times b1 should be equal to what? 3 over 8. And we can see it over here. However, we can also see here this residual that's on the complex axis. However, this is effectively a zero number. Similarly, if you multiply a2 by b2, you will also obtain 0.375. Let's check this. A plus b should be equal to 11 over 12. Let's see that. Here's the result. 11 over 12 is 0.96666, and we obtain exactly 0.999666. And over here, of course, we have an imaginary part that's equal to 0. Next, let's compute the control algorithm parameters. We set k is equal to 24, and we simply compute the constants of the PID controller. That is, we use this equation to compute the constant. This is the constant of the integral action, constant of the proportional action, and the constant of the derivative action. And here's how we do it in Python. Here the constant. We just need to select this part, And here they are, 9, 22, and 24. Going back to the post, here they are, 9, 22, and 24. Perfect. Let's continue. Let us double check the final characteristic polynomial. Over here, I will take the computed control parameters and I will substitute them in the characteristic polynomial given by this equation. I should obtain something like this, and the zeros of this characteristic polynomial should match the desired pole locations. Let's do that. Over here, I compute the coefficients. I define my polynomial. Here it is. We can also see it. 26. And the other terms are here. 1, 9, 26, 24. And let's look at the roots. Here they are. The roots are -4, -3, and -2. Forget about these small complex numbers since they are at the numerical precision. And that's it. Simple as that. Next, we need to substitute the controller and the open loop transfer function in the closed loop transfer function. And as the result, we obtain this equation. This equation is very important. We can observe two things. The poles are given over here, and these are the desired poles, so nothing is wrong over here. However, we can observe that we also have zeros. To remind you, zeros are zeros of this polynomial in the numerator, and the zeros are given over here. We can see that the real part of this zero is very close to this pole. Okay, to summarize, we observed that we have achieved the desired pole locations. However, we also introduced zeros in the controller. The real part of the zero is close to -2. Zeros will introduce some oscillations and overshoot in the system response. We will confirm this later on by using simulations. Let's simulate the system. To simulate the system, I'm using the Python Control Systems toolbox. This is a very powerful control systems toolbox. It's completely free, and I made several tutorials on how to use this toolbox. Links to my tutorials are given in the description below. First, let's compute the step response of this system. The step response is given over here. We can observe two important things from this step response. First of all, the steady state error approaches 0. This is because the input signal is 1, and in steady state our system tracks 1. Perfect. However, we can see this phenomenon over here. That is, we can see an overshoot. And as I will show it in 1 second, this overshoot is a direct consequence of introduced zeros in our control system. To see that, let us modify our transfer function. Here is our original transfer function, and let's eliminate zeros from our transfer function. We do that by simply dividing this transfer function by this term over here, and we multiply the result by 24 to obtain this expression. Why introduce here 24? Well, I introduced 24 since I want to make sure that my steady state DC gain is equal to 1. And let's compute the step response of this system. Here is the step response. We can clearly see a very nice and smooth step response. This is because we don't have zeros over here. And this system exactly behaves according to what we want. That is, we want poles to dominate the system response. That is, we should see the terms in our step response having this form, plus minus minus 2t plus minus e to minus 3t and plus minus e to minus 4t. That is, we should see something that looks like the response of the first order system. Next, I will explain the Python code that I use to simulate the closed loop response. I'm using the Control Systems toolbox. To install the Control System toolbox, you will need to type in your command prompt pimp install control. And this will install the control systems toolbox. Okay, first I need to import the necessary libraries. I need the plotting library, I need the control system toolbox, and note over here that the control system toolbox is imported as CT, and I need NumPy. Over here I wrote a simple function that is used to plot the results. This function accepts several arguments. It accepts the time axis vector, the y-axis vector, the title of our plot, the X label, the Y label, and the string file name. This input is used to give the name to the saved file. This function will plot the graph and it will save the graph in this file. That is, the name of the file is specified by the user. Okay, so let's define our transfer function. First, let's erase this part and let's clear this part. Here's how we do that. We simply specify s to be a complex variable. We call CT, this is our control systems library object. We say transfer function dot s is equal to s. And here it is. We can simply define our transfer function. Here it is. To show it, you need to type print w. And here's our controller. Let's print our controller. Here it is. Next, let's define the closed loop transfer function. Here it is. And note what I'm doing over here. First, I will execute this part to show you. If you type print v closed, look what you will get. Very complex expression. Let's go back to the tutorial and let's see our transfer function. The transfer function should look like this. However, we obtain something like this. Well, you need to cancel some zeros and poles over here, and to do that, you need to call this method minReal. And consequently, that's why I'm defining the transfer function like this. And once I do that, let me print the closed loop system. Here it is. Perfect. And let's simulate the step response. First of all, we need to specify the time vector, 0 until 5 with 100 steps. And over here, I'm calling the step response function. I specify the name of the transfer function, the time vector, and as the result, I will obtain the time and I will obtain the output. Let's see the output. Here it is. And let's plot the step response. I'm calling the function that I defined at the beginning of this video tutorial. Here it is. And voila! Here's our step response. Again, we can see an overshoot, and this is the phenomena that we don't like. However, we have to live for the time being with this overshoot. Let's compute the poles and zeros of our transfer function. Here are the poles, and here are the zeros. Perfect. Now, let's define a new transfer function without zeros. To do that, we simply divide our closed loop transfer function by this polynomial, and we multiply the result by 24. And let's see our new transfer function. Here it is. It doesn't have zeros, and the poles stay the same. And let's finally simulate this modified transfer function. Again, we define the time vector. We call the function step response. We specify the name of the transfer function, and we specify the name of time vector. And let's plot the response. Here it is. Voila! The response is very smooth. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot and have a nice day.